or emitter, right? Input goes to base or emitter, which one?
Base.
Output is from emitter, right? Why don't we do it the other way? Because you never take the output from a base. So already we know. So a common collector stage, usually collector is directly connected to your, if it is an NPN, your most positive supply. If it is a PNP, your most negative supply. There is usually nothing in your collector circuit, so I'm just connecting it to VCC. Your input is applied to the base, and the output is taken from the emitter. For biasing reasons, we usually have a resistor with the emitter terminal. Okay? So this is your core stage. This is the basic common collector stage. What is important to us? Input resistance, output resistance, and gain. Okay? So let's calculate those values for this circuit. Again, I'm assuming biasing is taken care of, right? So the device is happily biased. So I go from here to my small signal model, draw my transistor first. And then attach everything else I have. Collector is connected to VCC, it's going to be AC ground. Emitter is connected to RE, then ground, and Vin is directly connected to my source. So, and note that Vin in this case is not a label, it's actually a voltage source. Right? So you can, if you want to be explicit, you can just draw it. But it's not just a label, it's a voltage source that we attach it to. And the output is taken from across, is from the top of R. Okay? Let's do input resistance first. So how do I do that? Well, actually, no, let's do gain first. Gain. So let's do gain first. I want to find AV that is equal to V out over V. Okay? So I look at my circuit, V out is the voltage drop across RE. I can find it if I multiply RE by the current that goes through it. So what is the current going through RE? It's this current plus that current. They add up, go through RE. What's the current from the left side? The right side is easy, GMV pi. What's the current from the left side?
V pi over R pi?
V pi over R. Right? I write it this way because I'm not going to introduce a new variable I1 and then figure out that I1 is equal to V pi over R pi later. I know the voltage drop across this guy. I know the resistor. The current is V pi over R pi. Good. So I don't know V out and I don't know V pi. I need one more equation. And actually, I don't have a relationship between any of those and VA. I want to find, at the end of the story, I want to find V out over VA. So I need to find one more equation that hopefully doesn't introduce a new variable and also brings VA into the mix.
Just draw KVL from the inside down.
Yeah, so I can write a KVL in this loop. Yes, so all done. V in is equal to V pi plus V out. Right? All done. So if I eliminate V pi from these two equations, just put V in minus V out for V pi, I have everything I need.
Oh, sorry? AC is V.
I'm going to do one approximation here to make my life easier. GM V pi plus V pi over R pi. This is I collector plus I base, right? V pi over R pi is I base.
Yeah.
GM V pi is I collector. Or
Beta.
you can use formulas. This is GM plus GM over beta. R pi is beta over GM. So 1 over R pi is GM over beta, right? So this term is much smaller than this. Beta is 20, 50 if you're unlucky. Typically it's 200, 300. So this V pi over R pi term, and I actually, so at the beginning, don't make these assumptions, but over time, you'll see where you can make these kinds of simplifications. This one is much, much smaller than this. I'm gonna ignore that. You know, less than 1% error, I can live with that. So V out is GM RE, and they already got from the second equation here, I find that V pi is V in minus V out. I'm done. Okay? What can you say about this game?
It's not very deep.
Yeah.
No.
What is it in limits? Around 1, right? It's always less than 1. Huh. That's not the limit. Gain is less than 1 for sure. We already have the proof. Why is that? You should be able to see, well, I'll show it to you. But that doesn't really look very promising. Let's look at the current as the object. Okay? So to see the current as the output, what I do is that I go and short the output to ground, and I measure I out. And I look at the current that comes from the source. Okay? If I do that, so this is I out over I in. If you look at I out, if I short it to ground that node to ground, it's still going to be GM V pi plus V pi over R pi. Right? All of that current now goes to ground. And then let's divide I out to I in by the way. So that's I out. What is I in? Yeah, so what is, how much is it?
V pi over R pi.
V pi over R pi. And if you do the math, this is beta plus 1, right? Because, you know, you cancel V pi, it's GM plus GM over beta in the numerator, and then GM over beta in the denominator. So it has a good amount of current here. And that's why it can act as an amplifier. It can increase the power delivered to the load. Because the power is V times I. My output voltage is more or less the same as my input voltage, but my output current is much, much bigger. So I'm happy with that. So this can be an amplifier. So it gives me a lot of current. Could I see the current gain before? Yes, because it's the emitter current over the base current. I didn't have to do all that math. Emitter current to the base current. If I short the emitter, it's the emitter current to the load. And what is going in? It's the base current. So that's beta plus 1. I didn't have to do that, right?
So it's a current amplifier. More.
It's a current amplifier. Well, it is an amplifier,
Yeah, in
but
terms of
it's
power.
the power amplification comes from the current part, not the voltage part. Your voltage gain is always less than 1. At best, and when we saw this GMRE is 5, 6, 10. So this is close to 1. This ratio is 0.8, 0.9, 0.95. It's close to 1, but it's not 1. But I should have seen this too. I should have seen that V out is not going to be much different from my V in. How could I say that without any of those calculations?
That's just voltage drop.
Because the voltage drop across VBE on is around 0.7
Yeah.
volts.
It's constant, right? So your V out is essentially tracking your V in. The difference is DC. If you look at the DC difference, it's just 1 VBE. It's going to track, because remember, this is small signal, right? I'm not affecting the bias point. I'm not changing the current somehow, or the voltages somehow, that this VBE changes significantly and I go into, I don't know, a region that is very far from my bias. I'm resting or moving up and down here with my bias point. So that VBE is more or less constant. And what happens is that your V in is going up and down, your V out is going to track it by the same amount. 1 VBE less. Why is it less than 1? Why is the ratio is less than 1? Well, because for the small signal source, a portion of that signal drops across this resistor and the rest of it here. So there's always a little bit of waste. Your ratio will be less. Not all of it will show up at the output. But it's not a lot that you lose. Okay. So it's an amplifier. It's a current amplifier. And we found the gain. So this is AE. What about the other properties of this amplifier? I'd like to know the input resistance. So let's get rid of this short here, that's a different circuit. I have to know the input resistance. What's the input resistance?
It's the voltage of the
Yeah, you attach the test source and you do all the hard work. You don't have to. You've already solved that circuit. What's the difference between, from the input point of view, between this and a common emitter? Nothing. What was the difference between common emitter and this? You had a resistor up here. After the current source, nobody over here will even know about it. Right? So that resistor that we had in the collector circuit has no effect on what is happening down here. So your input resistance, do the math, do the calculation, but it's this much. We have that for the common emitter stage as well. Let's say you forgot about that. And then you want to do the calculations. You want to make sure that you do not trust your memory, you forgot your notes or anything. Okay, if you have done the gain calculation already, how do I do the input resistance calculation? I remove the source, I attach my test source, I look at how much current comes from it. But look at this circuit. Why can't that V in be my test source? There is no output resistance over there, right? I can just use all the calculations I did here for the input resistance part as well. Save a little bit of time. Because my source doesn't have any output resistance, I can do that. If I remove this voltage source and put Vx here, nothing here is changing in my equations. So I may as well use what I have here. So in general, in many cases, when you do calculations for input resistance and gain, the two are very similar, especially if your source doesn't have an output resistance. If it does, you can still take care of it, but if it doesn't, you basically are solving it the same way. So you have V in, you have I in, that is V pi over R pi. You know what V pi is from this equation, plug it in, you get this. Okay? So I'm not going to do that. So far, we have an amplifier with a large current gain about beta, a voltage gain of less than 1, hopefully close to 1, 0.8, 0.9 is typical, right? But a little bit less than 1. But the current gain will compensate for that. And a large input resistance. Large input resistance I like. Small voltage gain, I have to live with it. I don't like it that much, but I have to live with it. Large input resistance I like. Large current gain I like. Let's see how about the output resistance. So what if I look back into the emitter of this guy and see what I have from the output? So in that case, I have to using new small signal circuit, it's not going to be this. Because I'm removing all the independent sources here, meaning that this guy is grounded, and I'm attaching my test source here. So it's a new circuit, I have to redraw it, and do all the work necessary. So transistor first again. So I need to find Ix. And Vx over Ix will give me the output resistance. How do I do that? You're trying to find the current, usually KCL is your friend.
Isn't it? Would it be the current source plus the current across our pi?
No.
No.
No, this time we have to wait. So I already KCL here. I guess no. So Ix, that's the current that is entering the node. This current is going to add up to this plus that plus that. Right? And the three currents that are going out. So Ix is equal to, this current is Vx over Re. Right? This current is because the voltage from here to here is Vx, the resistance is R pi. Okay, so GNP pi is flowing this way, I imagine the current in that direction, so it's minus GNP pi. Okay? So Ix and Vx, I know I have an unknown V pi. What is V pi? How do I find V pi?
Vx.
Hmm?
It's equal to Vx, is it not?
Minus Vx. Right? Because I'm applying Vx to the bottom of V pi.
Oh, sorry.
So R pi. So V pi is equal to minus Vx. And then I have a relationship between Ix and Vx. So Ix is equal to Vx times 1 over Rv plus 1 over R pi plus Gn. Okay? And then Vx over Ix, your R out is Vx over Ix. And that's 1 over Rv plus Gn. And then I'm back to the same situation I had before. Gm plus 1 over R pi is just Gm. Right? 0.5% error. Because R pi is beta over Gm. Right? So I ignore them, so it's just Gm plus 1 over Re.
That's our pi.
And if you want to make this look good, I don't like it this way. Okay. Look at these two terms. So it's 1 over Re plus Gm. If I assume 1 over Gm, Gm is transconductance, so it's the unit is 1 over resistance, 1 over ohm, right? So if you assume 1 over Gm is a resistor, then I can see that it's 1 over Re plus 1 over Gm. It's as if I have Re in parallel with Gm. So I write it there.
Oh yeah.
Right?
Yeah.
I like this expression, I'll show you what in a second. But just keep that in mind. That 1 over GM in a lot of equations that we write from the past or from now on, you can look at 1 over GM as a resistance in your equations. And just simplify your equations based on that, right? But there is actually a resistive connection. Why? Because what is the input resistance when I look up the emitter? Forget about RE. When I look up the emitter, it's R pi in parallel with R pi in parallel with GM over R pi in parallel with 1 over GM. So if you calculate the input resistance when you look up the emitter, it's about 1 over GM. Ignore R pi. It's 1 over GM when you look up the emitter, right? So it's the input resistance when I look up the emitter in parallel with what I have down there. So that's another way I like to write it this way. If you go back to the transistor equations we had before, we said, when you look into the emitter, what do you see? You see R pi plus RB, whatever the base resistance is, the whole thing divided by beta plus 1, or beta, right? R pi over beta is 1 over GM. And in this case, you don't have an RB, so RB is 0. So when you look into the emitter, you see if the base is grounded, you see just 1 over GM. When you look down, you see RE, therefore the output resistance is this in parallel. Is it large or is it small, that output resistance?
Small.
Well, let's look at the numbers. So GM for 1 milliamp of current is about 40 millisiemens, right? So 1 over GM is 25 ohms. It's 25 ohms or 1 milliamp of current in parallel with RE. It's tiny. Your output resistance, if it is 100 ohms, 200 ohms, 1 kilo ohm, it's going to be dominated by 1 over GM. Right?
Small.
This guy has a small output resistance. And then if you want to make it smaller, if you want a 2 ohm output resistance, bias it at 10 milliamps. You get 2 ohms. Right? And then so on and so forth. Right? So it gives you a small output resistance. This is a stage you usually see just before the load. Just before the load, you have a motor, you have a speaker, you have something that needs a lot of current. You want something that gives you a lot of current, but has small output resistance. You don't really care about the voltage gain anymore, because all the voltage gain usually comes from the earlier stages. You just want to push a lot of current into the load. And you also, you can do the same thing with the common emitter stage. If you bias it at really, really high currents, and then you can do it, but you're going to waste a lot of energy. This guy wastes a lot of current, a lot of power. This guy just does it naturally, right? So a common collector stage is extremely useful. If you know these two stages, you'll be happy 95% of the time. You have a stage that gives you all the good voltage gain that you want, and if you want current gain, you can use 2. At the input, after your source, you put a common emitter stage. At the output, if your load is small, if it draws a lot of current, you put a common collector stage. What is another advantage of using this common collector stage? Well, you just saw that. You ever run on the bar? No. You just saw here that if you connect your load directly to your amplifier, your gain is dominated by these two in parallel, right? So if your load is small, your gain will drop, right? Because let's say if instead of 10K, if this was 1K, 1K in parallel with 6K would be much smaller than 10K in parallel with 6K. Your gain will drop because my gain is R5 in parallel with R1, right? So sometimes it's not that you want a lot of current for your load. It's just that you want to isolate your voltage gain or your voltage amplifier from the load so that it doesn't see the load, so that it gives you a lot of gain. In that case, what I can do is that I can insert the common collector stage here. What does that guy do for me? It gives me a lot of input resistance when I look into its space, drives the load, and my common emitter amplifier is now happy. It doesn't see a small load. It sees a large input resistance of that common collector stage. So in many cases, with these two stages, you can, if you do it right, you can satisfy the job requirements. The common emitter stage to give you all the voltage gain and everything else, and the common collector stage to essentially isolate your load from your amplifier. There is a name for these stages. We call them buffers. Now, have you heard about a voltage buffer? A voltage buffer is a circuit, is a component with a gain of 1. It just takes the voltage from here and puts it here. Why don't I short circuit the two to each other? Because of this. Because then, if I short the two, they will see each other, they will affect each other. But the voltage buffer takes the voltage here, puts it here, but the source here will not know about the load, and the load here thinks it's coming from an ideal voltage source. Right? Makes both sides happy. The question? Okay. Alright, so common collector stage analysis is the same as the common emitter stage and so on and so forth. So let's talk about the last possible topology you may have. The common base. And here is my transistor. So tell me, what do you think the input and outputs are connected? How they are connected to this? Input is to collector or emitter, because common base means that base is not in my signal route. So, emitter or collector for the input?
Cluster.
Hmm?
Cluster. No, look at this.
Emitter. We never connect an input
Yeah.
to a collector.
Yeah.
So, input to the emitter, output from the collector. The common base stage looks like this. Actually, we usually have an emitter resistance for biasing reasons, that we just include it here. This is your common base stage. And again, I'm ignoring biasing. It's biased and the not. I don't have to solve this circuit to guess some of its properties. Tell me, what do you think about its output resistance, large or small?
Well, I would say it's.
So the output resistance is,
Oh, sorry, that was this.
I think it's pretty small, that's basic. Oh, wait.
No, but it's not that.
No, it's just ours.
Common base is that.
R out. Do you think it's large or small? Depends on RC, it's RC. But usually it is large, right? So the common emitter scenario we had before, RC gave us the gain and everything. Probably large. What about the input resistance? I'm looking into the emitter of this guy. Large or small? Small.
This is in parallel.
It's just the calculation.
Yeah.
It's 1 over GM.
It's just a different.
In parallel with this RE. But it's a small input resistance. Right? What about the current gain? What do you think the current gain is going to be? So the current, if I send some current into the emitter and draw it from collector, how much is that current gain?
It should be small. It's just.
Yeah.
There's no.
At best, it's alpha, IC to IE, at best. Right? So it's less than 1. What's the Schottky stage? A current gain of less than 1. And a small input resistance and a large output resistance.
Voltage buffer.
The biggest voltage.
Let's just hope that it gives us some gain, some voltage. Let's just do the analysis and figure it out.
Yeah.
Let's just hope.
It's a non-resistance.
Otherwise, we're wasting time.
Large output resistance. That's the cap force curve everywhere. And you just said
Okay, so that's my circuit, and I want to find the voltage gain, V out over V in. So let's write V out and see what we need to find out. So V out is how much?
GMB pi RC.
GM V pi RC. Aftermarket. Current is going from ground up the resistor into that transistor. So minus GM V pi RC. Okay, so I need to find V pi, and I need to find the relationship between V pi and V in hopefully. So what do I do next? KCL at this node should do it, right? Do I need to do that?
No.
Why not?
Can't you just find GM through R pi with
What is V pi?
oh VM?
Uh-huh.
Come on, stop being so.
So I don't need to do any more, to write any more equations. I'm done. I found the out the main ratio.
Thanks.
Okay, so done. AV, V out over V in is GM RC. Okay. So the two negatives cancel, right?
Yeah.
So there is some hope. The voltage gain from this stage, the intrinsic voltage gain from this stage, is as much as the common emitter. The common emitter will give you the same amount of gain. Difference is that the common emitter will give you a negative gain. This guy gives you a positive gain, but the same amplitude, same amount. But the other parameters are really not that good, right? So the input resistance is small, output resistance is large. Yeah, I don't need, but let me just write it so that you have the records. So R out is RC. And if you want a lot of gain, you want to choose the large RC. If you choose a large RC, your R goes up. Right? Right? It should be R in is that RE in parallel with 1 over GM. And the current gain is IC to IE, and that's half, less than 1. Around, but less than 1. Do I need this stage? Or why would I use this stage? Any idea? I use it.
So your buffer? Your buffer?
Yes.
Well, the voltage gain is large. It's not a buffer anymore, right? It's not 1. It can be large, obviously, right? So, because GM is 0.4 for 1 milliamp, if you choose a 1K resistor, that's a gain of 40 right there. You can have a gain of 1, and you don't get a gain of 1.
It's a financial gain. We don't have the negative AV.
But the negative, we don't really worry too much about it. It's a financial loss because you're paying for components and you're not getting money. You could do better with the common emitter, right? So if instead of this, you make a common emitter stage, you can get the same gain, a high input resistance, and a current gain as well. And the output resistance is the same for both anyway.
Does it something to do with power? Because if the power is the same, just the voltage is higher and the current is lower?
No, same thing with common emitter. So we are not covering it, yes. True, but we don't really have too much use for those. But true. We don't cover it in this course. This stage has two advantages over common emitter. One is when you use this circuit, you can amplify larger voltages. You can handle larger voltages at the collector of this device. So if you look at the old TVs that had a CRT that needed to scan an electron beam across the screen, well, you have to use an amplifier. That amplifier is amplifying hundreds of volts. It's a common base stage that we have because it can handle larger voltage compared to common emitter. That's a rare situation. The main advantage of common base to common emitter is its frequency response. For the same resistor, same gain, similar components, this has a much higher bandwidth compared to the common emitter stage. So when you look at RF circuits, you see more common base than common emitter. Right? There are more high frequency amplifiers that you make using this stage than common emitter. For RF stages or for RF applications, it has another advantage that we like. The small input resistance is an advantage because in RF, everything has to be 50 ohms or 75 ohms or something in that range. An input resistance of 50 ohms for a common emitter stage basically is probably going to kill all of your gain right there. But for this guy, it gives you a small input resistance, 50 ohm, no problem, bias me at half a milliamp, right? So 50 ohm right there, and gives you a lot of gain. So the main application of common base is for RF applications. Typical low frequency applications, I would say with modern, the transistors you can buy off the shelf. Old ones like 23904, 23906, up to a few megahertz, you'd be happy with common emitter and common collector. If you want to go to hundreds of megahertz and gigahertz, you can still be happy if you find the right transistor with common emitter and common collector. But you have to find the right transistor. Right? So it doesn't have a lot of applications. You don't see a lot of it around, but it's a useful stage nonetheless. It has its own applications. Okay, so that's a common base stage. Let me see if we missed anything in this chapter that we have to cover. So okay, one more point. The other name for a common collector stage is emitter follower. If I was there in the naming ceremony, I would probably call it base follower because the emitter is following base, but then the other name is emitter follower. So if you see an emitter follower, it's a common collector stage.
Okay, let's go for that. You skip Muhammadan on.
Okay, so I can see that the rest of the slides are just examples and we have fun and answers for some of them, so it's all good. How do I bias a common base stage? I want to very quickly mention it and just go and do a full example on a common collector stage. Biasing for common base stage. So you have your RC, you have your RE, and you have your H biasing. You can use all of those techniques that we learned before for biasing a common base stage, a common base stage. You want to connect your source to the emitter, but almost never you connect it directly. It's always through a capacitor, right? Because as soon as you connect the source with 0 DC, you're grounding the emitter. So it's almost always connected through a capacitor. And the output is usually, not always, but usually taken after a capacitor. So that's your biasing and everything else for a common base stage. But how was the base connected in the basic figure I showed you? This is my common base stage.
Yeah.
The base has to be grounded. So what do we do? For AC, base has to be grounded. DC can be anything. Okay, so I bypass the two resistors that I have for DC biasing because I want the base to be connected. That's actually very important, right? So common base, if you ever design it, if you leave any of that RB here, you're going to have a lot of noise, a lot of performance issues, a lot of bandwidth reduction because of that. So you want to make sure that you have a good capacitor here. Sometimes you use a couple of them just to make sure that the base is connected. So if you use two, usually you use a big one like 10 nanofarad, 100 nanofarad, 1 nanofarad, depends on the frequency. And something that is about 100 times to 10 times smaller. So if you're using let's say 10 nanofarad capacitor here, use 100 picofarad capacitor here. Because usually the big capacitors have big parasitics as well. So the small guy is going to help this guy behaving more like a capacitor as well. So that's common base bars. Let's do an example of the common collector state. This is the common collector stage, right? Input going into the base, coming out of the limit. Doesn't matter if it is NPN or PNP, same. So let's just use some numbers here. Let's assume the data is 300 like what we had before. VV1 is 0.65. VCC is, I don't know, 3 volts. Okay. So let's find out. And then, you know, of course, you can have a capacitor here and a load and all that. So it's a relatively simple problem. First thing we do is we find the operating point, the bias point parameters, writing KVL from VCC to ground. So I'm not going to ask because I think you all know how to do all of that by now. Okay. So IE is beta IB, so I'm just going to find IB from here. So this is a biasing technique that we said, you know, it's okay to use if you're making 1 or 2 circuits, but in general, this is not super stable, right? It depends on beta. But if you're making 1 or 2 circuits, it's okay. Otherwise, you want to use H biasing, that's your go-to method. So I put 1 resistor at the top as well, and form an H. Anyway, so this is easy enough. So IB is going to be 3 minus 0.65 divided by, for RE, how much is it? 450 ohms times Q1 for beta plus 1 plus IB, 100K. So you can do it right. This is 9.98 microns. 10 microns. Right? And then from here, IC is going to be 3 meters. And you can check that the device is working. Now, for all the gain and everything else, we need to draw the small signal. For a PNP, the small signal model is exactly the same as an NPN. So when I draw that GN pi here, plus or minus V pi here, R pi here, collector is grounded, emitter is connected to RE to ground, VCC, the other end is ground, and base is connected to my source through a capacitor, which is now short circuit. And I have RB hanging from here to the ground.
It's times 300. Even though it's not 0 times 5.
To solve, who is confused?
Oh,
I heard confused.
I said I don't like PNP.
I use the word PNP.
The 301 is beta plus alpha.
Beta plus 1.
And that's a times, not 450.0, right?
And that's times, yes.
Yeah.
Sorry, sorry. Yeah, this is not this is times. Okay, so that's my small signal. I can go and find the out the way we did it before and solve. Or I can use my formulas. Yeah? Because I can reduce this to a core common collector stage. From base to emitter, if I look in between these two nodes, that's my core common collector stage. I know the gain for it, I know the input to resistance, I know everything. Right? So what I can say is that from the equations, from the solutions up here, this is my gain. GMRE over 1 plus GMRE. So over here, I can say that if I call this VB, I can say that V out over VB is GMRE over 1 plus GMRE. Right? Good news, the VB is the same as VA. So I don't really have to have all those voltage division and everything else that I did before. Why? Because V in doesn't have an output resistance. Whatever voltage I have at V in is directly applied to the base. Right? There is no voltage division. In that case, now we can see that RB doesn't affect your performance. Okay, so let's find values. So for 3 milliamps, GM is going to be about 75 milliamps. So 75. So if I do the math, this is 33.75 divided by 1 plus 33.75. And that is 0.97. So I usually write the unit as volt per volt to just indicate that this is a gain. This is not just a random number, it's a gain, a ratio of 2 voltages. Okay? And that's going to be my V out over V. So life is easy in this. Good. What about the input resistance? What is the input resistance of this circuit if I want to use the formulas? 2 minutes.
Is the RB with parallel with R pi and RE?
So it's, I don't know from here, but I know it from here. From here onwards, it's R pi times 1 plus GMRE, right? Before that, I just have one resistor to ground. So this is the input resistance of my stage. That's what I see when I look into the base. Let's just call it RID. Right? That whole thing is in parallel with RD. Okay, so RB in this case affects my input resistance but doesn't affect my gain. My input resistance is. What about the output resistance if we want to add it?
Yeah, I don't know.
So for output resistance, you remove your source, you zero your source. Zeroing your source means that you have short circuit ground at your base. This RB guy doesn't show up. Okay? Because if you open it, RB will appear in your base signal. You don't open it. When you're calculating the output resistance, you zero your independent sources. Zeroing this source means that this is grounded. Ground here means that RB is not showing up in your circuit. And then what is R out? Well, it is 1 over GM here, RE at the top. So in this case, because we are biasing at 3 milliamp, this is around 8 ohms. RE is 450, so it's about 8 ohms. That's really small for most applications. Okay, time's up. Any questions?
There's no Tesla Friday, right?
You want to?
No.
No test on Friday. No, the schedule is whatever we have on campus, right? So we have a quiz next Friday on BJT amplifier. So this is it. We are done with BJTs. From next lecture, we're going to talk about MOSFETs. Okay? So the stuff on the quiz will be everything that is about BJT.